So we're going to start talking about second order differential equations now, and we've already seen some idea of why second order differential equations are a little bit more complicated than first order equations. From this phase space point of view, I mentioned, I think at the beginning, that you can take any second or third order ODE and convert it to a system of two first order ODE simply by changing or introducing additional dependent variables. Now, that sort of hinted to us that the dimensionality of the space, so the number of simultaneous first order ODEs that you have to solve, goes up, and so the dimension of this phase space presumably goes up, and that's possibly the reason why, as you go from first order to second order, things become more complicated. That's a geometric picture that is useful to keep in mind. But today we'll start with second order systems, and there is an algebraic way to also see where this complexity comes from, which is what we'll do. And let me first, before we start, let me outline what it is that we're going to talk about second order systems. Okay. So first, today of course I'll talk about why are they more complicated. That's what we'll discuss today. And then we will talk about linear second order systems. We'll spend quite a bit of time on linear second order systems for two reasons. One is, well, it follows from the answer to the first question, which is second order systems are complicated. So linear second order systems are also much more complicated, much richer than linear first order systems. So that warrants more time. That's one reason. The second reason why we'll spend time on this is because it's useful when you actually do this procedure of linearization. Okay, and linear second order systems come up in a number of different contexts. They come up in the nonlinear context, like I said, when you do linearization about a fixed point. We'll look at some examples of how to do that. But lots of examples are second order linear systems. For instance, spring mass damper motion is something you've probably seen before. That's a second order linear system. And Newton's laws of motion, second order system, right? Everything is second order. I mean, elasticity, waves, they're all second order PDs, which can be in some suitable configuration reduced to a second order ODE. And so this will provide the starting point for understanding general behavior of second order systems, which is why we'll spend some time on it. Okay, and then I'll briefly talk about phase space. And bifurcations in phase space. We'll talk about this briefly because it's important, and although the ideas are algebraically more complex, they're also geometrically more complex, like I said. The basic notions that we've introduced in the context of first order systems should suffice to get started with this. So we'll get this sort of going, and then at the end I will talk about series solutions and numerical methods. Okay, so I would think about 4 sessions on these, and maybe 2 sessions on these. Okay, and series solutions really are the starting point for more advanced techniques that you will probably learn in a more advanced course, perturbation techniques, asymptotic expansions and things like that. Series solutions are the starting point, so it's useful to look at them. Also, series solutions are important because they bring the connection with PDEs to a sort of completion. We started from PDEs, we made the thing ODs, and then we went around. And presumably, if you're going to come back and close that loop, you have to look at series solutions for the ODEs that arise from PDEs, and things like Bessel functions and spherical Bessel functions, spherical harmonics, and so on are all covered under series solutions. We'll see a few examples. The procedure is fairly standard. It just involves expanding stuff in a series and then evaluating things term by term. But it's an interesting exercise to go through so that you know exactly how it works. Okay, so that's our plan for second order systems. Okay, so let me start with this the simplest second order system that you can probably dream up. This is a linear second order system. And let's ask the question, why are linear second order ODEs difficult? Okay, why are they difficult? First order linear ODEs are trivial. We already saw that. You can use an integrating factor and just basically get a solution in closed form, and you can be happy with that. But you can't do that for second order linear ODEs. Okay, and we're going to see why. Now, usually, if you look at the way linear second order ODEs are presented, for instance, if you look at the textbook Boyce and De Prima, it at first glance you can just come across as being a series of substitutions or techniques or special tricks and so on that seemingly are just pulled out from a hat. Okay, but the reason that is so is because of the wide variety, first of all, of second order ODEs that you can have. But more importantly, there is no general way of solving a general linear second order differential equation. So there is no general formula. Okay, but let me write this down. So general linear second order ODE is going to look like this. This is the general linear second order differential equations. The coefficients can of course depend on t in some nonlinear manner, it doesn't matter, but the differential equation is linear because you don't have terms that are nonlinear in y or the derivatives. And there is no general formula to solve this. Okay, if you compare this, if you do versus the general linear differential equation from the first order, it looked something like this. Okay, you get rid of this, you divide it and you change the names of these coefficients, whatever. I'll just call them P and Q. Maybe I'll call them P1 and Q1 just to differentiate them. This one we could solve in general, right? So you could write down E y is equal to whatever stuff and with e to the power of minus integral Q of t dt, whatever, right? Integrating factor P times Q, whatever. Okay, you had an integration factor. So you could actually write down an expression for y. I mean, the integrals could be complicated, but you could still write down this expression. Now, there is no equivalent over here. Okay, there's nothing you can do that is analogous to that. So it's always I'll write this down, general integration factor. So it's always a little bit more cumbersome when you don't have recourse to a technique like this, even for, notice, the simplest linear second order system. Okay, so that's where the problem starts. Now, if we say, okay, let's look at a second order differential equation that's homogeneous. So if I look at the homogeneous version of this, homogeneous basically is R of t is equal to 0. So I only have the left hand side. I'm going to just rewrite that as like so. Okay, this is a homogeneous second order linear differential equation for any arbitrary coefficients, again p, q of t, functions of t. And how do you go about solving this? Okay, that's the question you want to ask. Similar to that, how do I go about solving this? The most naive thing you can do is probably to, in order to reduce the derivative, presumably this is the problem because the second derivative and the highest derivative here was 1. So if somebody naively came and said, okay, the second derivative is the problem, let's get rid of it. So you could try to integrate the entire equation with respect to t ones to make sure that the highest order derivative is like this, and then maybe you can do something about it. If you try that, then you integrate term by term, you will get dy by dt plus integral p of t dy by dt dt plus integral q of t y dt. equals 0. Okay, now okay, maybe you've brought it to something that looks a little bit better in terms of lowering the order of the differential equation, but what have you lost at the expense of that? It's this. So now you have the unknown y inside an integral, and so this now becomes a integral differential equation or a differential integral equation. Okay, so this is not going to work. So the naive idea of lowering the derivative to make it easier to solve using some scheme like this is not going to work. That's out of the question. Good. Now somebody else comes and says, okay, what if I were to factor this out? That's a possibility. Now the next more interesting, more maybe intelligent possibility. If I take this homogeneous equation, let me write it up here so that q of t y is 0. If I take this equation and I try to factor it out, okay, what do I mean by that? Let me call the derivative operator by d. I'm just going to denote it d. Then this guy presumably is d square plus p times d, p of t. Let's make this explicit, plus q of t times y is equal to 0. So this is quadratic in d, thought of in terms of this derivative operator thing, and then you could come and say, okay, this is quadratic, maybe I can factorize it, maybe I can express this as d minus d plus a of t times d plus b of t, the whole thing acting on y equals 0. That's one possibility, you could work that out. Yeah, that's looks easy enough to do. And if you do that, then things become easier because you have this guy acting on this guy giving you 0. So I can just rename, if this is possible, if we can do this for suitable a and t. Of course, a and b will be functions of p and q in general. If you can do this, then you can just rename this entire thing as w is equal to d plus b of t times y. That's another unknown function. I don't know what w is, but I'm just taking this entire thing, renaming it w. And so the only differential equation I'll have to solve will be d plus a times w is equal to 0, or if I just open it up, this will be dw by dt plus a of t times w equals 0. Okay. So if I could go from here to here, then I can rename this as w, and I'll just have to solve this first order linear equation for w, and I can do that quite easily because I know how to do that for the first order linear system. It's quite fairly trivial, right? I just have to cross multiply, I can divide, and then I'll get 1 by w dw by dt. Let me write it down. If I have dw dt plus a of t 1 by w 0, then I'll just integrate this entire thing. Of course, I'll get ln of w is minus integral a of t dt, similar to what I did here, of course, and then I'll get w is equal to some constant times exponential minus a of t dt. Okay, this is some constant, integration constant, whatever, doesn't matter. Okay, so if I break this down into a product of these two factors, then to determine this entire guy, I have to just solve this equation, which I've already solved. So I know what w is, and I can take the w and put it back here because I know the definition of this right hand side. So I'll get d plus b times y is w, and w is this. This, if I write d again as d by dt, I'll get dy by dt plus b of t times y is equal to w. Okay. Right hand side is a known function, left hand side is a first order derivative linear, right? It's a linear first order ODE with a known right hand side, which is exactly this. I know q, I know p, I know b because I have managed to factorize if subject to that. If I do that, then okay, then I can solve this. I have solved this to get this. Now I have to put this back here and solve this. I'll get y. That's it, right? So that means if I'm given some arbitrary differential equation like this, arbitrary linear second order homogeneous differential equation like this, I should in principle be able to write down the solution to the differential equation just in terms of the coefficients P of t, Q of t, because A of t and B of t after I factorize will be in terms of P of t and Q of t. Okay. If this were possible, of course, but unfortunately it's not possible. Okay, I'll tell you why it's not possible. The first reason it's not possible is the following. If I take this guy going from here to here, this step, let me call this step 1. Step 1, which is presumably this basic step upon which all of this stuff hinges, or hope of getting a final expression analogous to this for the second order case, hinges on step 1, and step 1 is not possible. Okay, I'll show you why in a minute. But before we get there, let me give you a quick example. So if I have an equation that looks like this, okay, this equation, let me get rid of this, now we know what this is. So let me write it down here. Let me say example. I'm going to look at the equation d square minus 1 times y is equal to 0. What equation is this? This is, if I replace that, I'm going to get d square y by dt square minus y equals 0. Yeah, that's, you know how to solve that equation, second derivative put on the other side, get exponential, whatever, that's fine. But assuming we didn't know that, and we wanted to go through this process, because if this process works for any arbitrary equation, it should work for that as well, right? So, okay, you come back, you look here and you say, okay, let me factorize this as a product of these two terms, just like I did with the A of t, B of t. Here, P of t is 0, Q of t is minus 1. Okay. So, let me factorize. How do you factorize? Well, the most naive way of factorizing this is to do this, because squares, right, d square minus 1 is d plus 1 is d minus 1, you could do that, y equals 0. That will work. It will work because you can try it out. You will see that you will get the solution. But the factorization is not unique. Okay, so I can also write this as d plus tan hyperbolic of t times d minus tan hyperbolic of t times y equals 0. Tan hyperbolic is the, I don't know if people know about the tan hyperbolic function, it's e power x minus this is tan, it's t, so it will be t here and t here, t. This is the tan hyperbolic function, right? E power t, e power minus t. So, if you take this and open it up, and what do we mean by open it up? You take d plus tan h t, d minus tan h t, and you expand. So, you take d and run it through the entire thing, you take tan h and run it through the entire thing. Then you will see that this will correspond also to this. Remember, when you run it, I would strongly encourage you to try it out. When you run this through, you have to remember that you have a y here. So, when you are running the d through, first term will be d square, second term you will have to do product rule. Okay, so, you will have d of tan h t times y minus or plus whatever d of y times tan h t. Okay, and so that will give you secant square, 1 minus secant square will cancel with tan square, and then you will see that the algebra works. Okay, secant square minus tan square, whatever, you have to use that relationship, you will be able to figure it out. But basically this will also give you this. So, the first step is already running into problems, right? This first step, factorization, is not unique, and it's not unique for functions like this. These are operators on functions, right? So, it's not unique for this case, even though it's unique for numbers. So, if I gave you like a number, let me pick a number like 143. Okay, I can write this 143 as presumably 144 minus 1, this is 12 square minus 1, this is 13 into 11. 11 into 13 is 143. Okay. So this is unique. Okay, for numbers this is unique, but for operators this is not unique. That's where the first problem starts. The first problem starts here. So our semi-naive idea of trying to factorize this and getting it to a first order system is already gone. Okay, it's not unique. But we say, okay, maybe it's not unique, but maybe one of the solutions will work. So this one, for example, for this case, this one will work. So why don't we try this? Okay, maybe one of them, maybe when you try to do this, you will get many A's and B's, presumably all different. But what if at least one of them were correct? So if I just work this out, I see whatever possible A's and B's I can get, at least the actual A and B should be hidden there somewhere. So I look for that, and then maybe if I look for that, I can reduce it, go through this entire process, come to W, and then solve for Y, and then write down stuff in closed form. You probably know the answer to this, but that also is not going to work, and I'll show you why. To do that, okay, what's the simplest way to do this? Well, the simplest way is to just famous movie dialogue goes, is just to do and ask questions later, right? And so that's what we're going to do. So let's start. I'll write this equation down again. Okay, and I'm going to say that, okay, this is again the if I'm going to have d plus, let me write this down like this. Okay, this is the same equation. I'm just going to write it down in terms of d square plus p times d plus q acting on y, like this. And d, p and q, remember, are functions of t. They're not constants. Okay, this is arbitrary homogeneous second order equation. So if I can do this, a of t times d plus b of t, then I'm in business. Then I can do whatever I just outlined over here at the bottom. I can just reduce it to two first order systems and then write down an expression for y with that, which will make me happy. So how do you do this? Well, you open this and you compare coefficients with this. Simple enough, right? So you do that, you'll get d square plus, now notice the example I gave you there is what you have to do here. D acting on this entire thing will give you b times d, because that will give you b times d dy by dt when you do product rule, plus b prime, because that is d acting on this, plus a times d plus ab, even y equals 0. Okay, so please make sure you understand why this happens. This is, if I explicitly write it out, this will be d by dt plus a, this entire thing acting on d by dt, dy by dt plus b times y, and then you open this up, you will get chain rule d square y, and then when you do this term, you will get, by the product, not chain rule, product rule, you will get d by dt of b times y, and then one will have a b prime times y, the second one will have a b times dy by dt. That's what this is. Okay, so please make sure this algebra is okay. Okay, good. So now we have this, we just have to compare. D square compare, that's okay, that works. What about d? So for d we need to have b plus a. These are the terms with d, this is the only term with d. So b plus a is p, small p, again function of t. B of t plus a of t is small p of t. I'm going to skip writing down function of t because I'm going to assume that they're all functions of t, some arbitrary function of t. So that gives us one equation if you compare this term, and this term. And the third equation we are going to get is in terms of q, and that will be b prime plus ab. Okay, so I have two equations, I have two unknowns, I can solve. Okay, that's about the easiest problem in linear algebra that you'll ever work out, right? Two equations, two unknowns, two unknown functions, okay, but whatever, it doesn't matter, right? Two equations, two unknowns, solve. How do you do that? Well, we get rid of one of them. Let's get rid of a from here. I'll have a is equal to p minus b. So and then I take this and put it back here. So I'll have b prime plus a being p minus b times b is equal to q. And then I'm going to get b prime plus pb minus b square, sorry, b square is equal to q. So this basically gives me b prime is equal to b square minus p times b, this is small p of course, plus q for the differential equation. So if I want to go from here to here, I need to determine a and b. If I solve this ODE now for b, then I can put this back here and get a, because I know what p is, I know what q is. That's the differential equation I'm given initially, right? So if I can solve this, I can put b here, I can get a. If I know a and b, I can break this into this. Okay, so far so good. We've started with the second order ODE, we've come to a first order for one of these factors. But you notice that it's not quite there, because this is first order, but it's non-linear because it has a b square. Okay. If it was first order linear, then okay, we're done, right? You just solve this, you'll get b. You solve this, you'll get a. You just put it back and you're done. But it's non-linear. So now what do we do? Now p and q are just arbitrary functions. We don't know what they are. If we knew what p and q were, maybe there was some hope of solving this non-linear first order ODE. But right now there is no such hope. If q was 0, then okay, you could do b of p minus, and then you could try something else. Maybe p were constant, you could do something, but no. In general, no. Okay. Now it turns out this equation has it's a famous equation. It's called the Riccati equation in 1D. This particular equation has a special name because it has a quadratic term on the right hand side. Okay, any term that has dB by dt equals some quadratic b square plus some b plus some constant, some function is equal to 0 is given this name of a Riccati equation. And people have studied Riccati equations from, I don't know, I suppose the time of Riccati. And when you see a Riccati equation, the standard thing that you will try to do is you make a substitution. That looks like this. Okay, if you see a Riccati equation, you make Riccati equation of this form, you make that substitution. Okay, so w is an unknown function, b of course is the unknown function we're solving for. So you make this change, b is minus w prime by w. You can do that because w is some arbitrary function, we don't know what it is, you have to solve for it. If you do that, then you will get b prime is minus w prime by w plus w prime square by w square. Yeah, and the right hand side will give you w prime's b square, which is w prime square by w square, minus p times b, which is b, which is w prime by w with a minus sign, so that will cancel with this minus sign, plus q. Okay, so far so good. So we have come all the way from here, presuming that we can do this. We have come all the way here, landed up at the Riccati equation, then you run to the library or to Google or whatever, and then you open up a handbook or you open up Google, you look at Riccati equation, and then it says, Riccati equation, this is the Riccati equation, you make the substitution, you can solve the Riccati equation. So you go and make the substitution, and then you just put this on the right hand side. Left hand side you will get this, right hand side you will get this. These two terms will cancel. And so b, this w now, which is the unknown, remember b is in terms of w, we have made a substitution. The unknown w now obeys this equation. Okay, from here, analogous to this. So now, okay, cross multiply, it's become linear. The non-linear term, the Riccati fellow, is gone. So now it's linear. So I multiply through it by w. I take this fellow to the right hand side, and then I get w prime plus pw. So if I solve this equation, then I can get W. If I solve this equation for W, I can get B. If I know B, I can put it here. I can get A. If I know what A is, I can factorize this. And if I can factorize this, then I can write down general expression for Y. Okay, I hope the logic is clear. What is the problem here? To solve this equation, we're back at our initial equation. So to be able to factor our initial equation, we have to solve the initial equation. Okay, so we're basically, we've tied ourselves in a knot. To factor, let me call this 1. To factor 1, this is 2, 2 is the same as 1, y and w are the same. I mean, if you replace y with w, unknown anyway, doesn't matter. To factor 1, we have to solve 2, also known as 1. So to factor 1, you have to solve 1, which really makes no sense because now we haven't really gained anything from this entire exercise. Okay. So we're back where we started, and so the consequence of all this sort of algebra throwing around that we've been doing is that you cannot go from here to here in general. Okay. Special values of p and q like the d square minus 1, maybe you can, but in general you can't. There is no way to factor. So there's no hope of obtaining a closed form solution for an arbitrary linear, it's not even non-linear, it's a linear second order differential equation, homogeneous, doesn't have an r of t on the right hand side. So even for that case, it's not possible to obtain a closed form expression at least, or something that says y is integral of some function of p plus some function of q plus something, right, like we had for the 1D case. You cannot do it, and that really is where the problem lies. Okay, this is, of course, if you think deeply about it, this is a consequence of this higher dimensionality of phase space that I sort of spoke to you about, but this is really where the algebraic problem lies. And that's why if you take a differential equation book, you will see chapters dedicated to just linear second order differential equations with arbitrary coefficients. Okay. This is presumably one of the simplest types of second order equations we can think of, the linear case, and even that has no solution that is analogous to the first order case. Okay, so that puts us in a bit of a fix. We have to find a way out of this situation. Okay, so what do? Well, we take recourse to this thing I've been saying repeatedly about this hierarchy of increasing order of hopelessness, which is the following. So the first thing, remember, we said when we started was, okay, always look for an exact solution. That's the thing that will give you all the dependence, all the parameters, whatever. And so you always look for exact solution. Now it's gone, unless it's a very special case, and you know special cases where p and q are constant. We presumably know how to solve them. We'll go over them quickly, but I'm sure you've seen that before. So unless you have that, you know, the exact solution is not going to happen in general. So this is out. The next solution is this quadrature series stuff, which I spoke about. That's also out because, like the first order case, we could at least do this, reduce stuff to an integral of something, e to the power of p of x, whatever, p of t, whatever, but we can't do that here. So this is also out. We can do what are called series methods. We'll talk about that, like I said, right at the end once we do all the other interesting stuff. So this is possible in some sense, and that's why series solutions to second order ODEs become so important. Okay, that's why Bessel functions, Bessel equations are all series solutions. It turns out you can write a series solutions for most linear second order differential equations if the coefficients are well behaved and so on, and they satisfy some constraints. And that's why you will see Bessel function, you know, trigonometric functions, you get series solutions for all of them. You can derive them from the differential equation. But if this fails, you can do what we said were semi-quantitative methods. Again, this is the phase space stuff. We did this for the 1D case. We'll do some of it for the 2D case. And if this fails, you're going to resort to numerical methods. Okay, that's basically what you can do. Now, there are a class of techniques that, like I sort of maybe mentioned briefly, that start off from the series expansion solutions, series solutions, and derive what are called asymptotic expansions or asymptotic approximations. They're a little bit more involved. They need some background in approximation theory and so on. But so obviously, in the interest of time, we won't go over them. But that's also something that you will eventually see: perturbation expansions, asymptotic expansions, and things like that. Okay. Good. Okay. So semi-quantitative, we'll do the phase space stuff. Phase space, again, that will come at the end. Numerical, of course, there's nothing to write here. Numerical methods for solving second order ODEs, I'll mention what those are. But we'll start here now, and then we'll go to the case where P and Q are constants, and then we'll see that you can solve them in closed form. Again, this is a standard trick. You will get a characteristic equation and so on. I will write that down quickly. And once we do that, we will then move on to some techniques for extracting solutions if some information is known. Okay, so I'll give you some of these ideas first for linear systems, and then we'll move to this, and then we'll come back here, and then we'll go here. That's our plan. Okay, so we'll start here for whatever it's worth, whatever we can solve in exact form. We'll come here, and then we'll go here, and we'll go here. So we'll change the topology of our hierarchy, but we'll still talk about these things. And this is sort of the increasing order of importance anyway. Good. Okay. So let's start at the beginning. So let me write this down in a more decent form without the operator notation. Let me write this down as d square y by dt square plus p of t So we'll start over here. Now, in general, this is a homogeneous equation. Of course, please remember this is homogeneous because it has no term that doesn't contain either y or its derivatives. That's what we said a homogeneous equation was. And in general, this has two linearly independent solutions. Okay, what do we mean by that? What do we mean by linearly independent? Well, you know what linearly independent are in a linear algebra sense. If I give you two vectors and I asked you if they're linearly independent or not, you just have to see if one is proportional to the other, or what direction they're pointing in. If they're pointing in the same direction, they're linearly dependent. If they're not, then they're linearly independent. Yeah, so you know, in a linear algebra sense, you know what this means. But what does it mean in a differential equation sense? Okay, it means the following. So if you have y1 of t and y2 of t, these are linearly independent if and only if this function w of t, which is y1 dy2 by dt minus y2 dy1 by dt, is non-zero. Okay, so you take y1 and y2, you look at this combination y1 dy2 by dt and y2 minus y2 dy1 by dt. If that combination ends up being 0, then the two of them are linearly dependent. Okay, you can check this quite easily. So, for example, if I gave you y1 of t is e power t and y2 of t is 2 e power t, then clearly they're it's basically the same apart from a coefficient. There's 1 here and there's 2 here. And if you put this down here, then you take a derivative, you will get e power t times, let me work that out. So for this, w of t is e power t, 2 e power t. 2 comes from here, and then I dy by dt of this, it just gives me e power t. Minus, if I do dy by dt of the other guy, I'm going to get 2 e power t, and that's 0. So these two are linearly dependent. Okay. So why is this important? Well, it's important for the following reason. Anytime somebody gives you a solution to the differential equation, let's call it y1 of t. So y1 of t obeys this. Okay. Then you can take any function that is a linearly dependent on y1. So for example, if I take c times y1 and I put it back into the differential equation, that will also obey the differential equation. Okay. Because c will go through all the derivatives that will come outside, and c times something that's already equal to 0 will give me equal to 0 for any c, right? So in principle, you could take y1 multiplied by some arbitrary number and generate infinite of them, but those are not giving you any information that is additional to what y1 is already giving you. Okay. So that's important to keep in mind. Okay. The other thing starts from here. Remember, I mentioned there are two linearly independent solutions. So y1 of t and y2 of t. And when you have two independent solutions, when you have two independent vectors in a vector space, what do? You can use them as a basis, right? If the dimension of the vector space is 2, then you can use any two linearly independent functions, any two linearly independent vectors as a basis for any element or any vector in that vector space, right? You've studied this in the linear algebra part. So the dimensionality here is 2, and you have two linearly independent functions, in which case you can write a general solution as c1y1 plus c2y2. Okay. So this is any arbitrary solution to this differential equation if y1 and y2 are solutions of the differential equation. Okay, why is that? Well, these two are arbitrary, of course, these are constants. Why is that? If I take this, we call this, if I take this y of t and put it in here, then again derivatives will go through unaffected by c1 or c2. All the derivatives will do the same thing, and then if I just add all the terms up, if I substitute that, you will see you will get c1 times this equation with y1 plus c2 times this equation with y2, and since y1 and y2 are solutions, each of them is equal to 0, so the right hand side will be equal to 0. So this y of t will in general satisfy that if y1 and y2 satisfy that. Okay, so that's how you build a general solution. Good. So we know something at least. If somebody gave you a differential equation like this, the task at hand is to find two linearly independent solutions. And how do you find the linearly independent? You check for the w. This w incidentally has got a name. It's called the Wronskian. Okay, w is called the Wronskian, and you try to find two linearly independent solutions such that the Wronskian is non-zero. Okay, and remember, Wronskian should be non-zero as a function of t. Okay, so it should be a non-trivial function of t. It can't be 0 for all t. It could be 0 for some t, but not all t. Okay, that's what linearly independent means. If you find a pair like that, then the general solution is written like this, and the constants, of course, c1 and c2 go into the initial conditions that we talked about. So remember, when we started talking about this, we said a solution, what we mean by a solution is basically, maybe I can get rid of this. What did we say when we meant a solution, which is that you have ODE 1 plus 2 what we call auxiliary conditions. These could be initial conditions or boundary conditions or whatever, right? We've discussed this. So this is ICs or PCs. Remember, in the first order case, we didn't have to make a distinction because you had to specify only one value, y at some t equals t naught. Now you have to specify two values. Okay, you can either specify both y and dy by dt at t equals t naught. This will be an initial condition, or you can do boundary conditions, of course, which is a combination of this. So you do y at t equals t naught and y at, let's say, t equals t1. Okay, that will be a boundary condition. Similarly, you could do, instead of this, you can just give the two derivatives at t equals t naught and t equals t1. That will also be a boundary value problem. Incidentally, this is called the Dirichlet boundary value problem. That is called the Neumann boundary value problem if you get the derivatives. Or you can think of a combination of this. You could give y at t naught dy by dt at t1, y at t1 dy by dt at t naught, and so on. So these are all mixed boundary value problems. So this is what we mean by a boundary condition, one of those three possibilities. This is what we mean by an initial condition. Okay, so please keep that in mind. So now, unlike the first order case, another thing you have to keep in mind is you have to make a distinction between which of these you are talking about. Are you talking about an initial condition specified with the ODE, or are you talking about a boundary condition specified with the ODE? And depending on which one you are talking about, the sort of analysis or techniques that you have to go through will be slightly different. Okay, we'll see more about that when we talk about the nonlinear case. Linear case, it doesn't matter so much because the only thing you need is two constants, and as long as I have y1 and y2, the only thing I need to evaluate the c1 and c2 are just one of these many possibilities. Okay, good. So you have two conditions, either these two or whatever, and you have two constants, so you can solve for them. And in principle, if somebody gave you y1 and y2, you can actually get the general solution that satisfies this entire system, this system. Okay. Okay. Now the problem is, like I said, you can't get two linearly independent solutions in general for arbitrary p and q. You can't write down y is equal to whatever, like we said, like we set out to try, but realized we couldn't. And so the problem is already in the first step. So if you are given two linearly independent solutions, you can do all this stuff and get the general solution. But if you don't have this, what do we do? And that's what we're going to spend some time trying to understand in the next maybe session or two. Okay, next maybe this remaining of what we have today and in the next session. So let's start with the simplest case. So the simplest case, which I'm sure you have all seen in some form before, either in a mechanics course or in an undergraduate ODE course. This is when p of t is constant. Let's call this p naught, and q of t is also constant. Let's call this q naught. P of t is p naught, q of t is q naught. Okay. If you do that, then your differential equation basically looks like this. It looks like this. And in the light of what we've said, maybe you can say a couple of things about this. We've all seen this in some form before. Okay, you have constant coefficient second order ODE, and then what do? You put, or as you have probably most likely seen before, you put y equals e to the power of lambda t, or RT. Let me make it RT. We don't have R there. RT. Put this, and presumably I've picked it out of a hat, and there's no a priori reason why you should put this, but okay, you put this, you will get a quadratic equation for R if you do this. So you will get R square plus P naught R plus Q naught times e to the power of RT is equal to 0, right, if I do that, and e to the power of RT is presumably never 0 unless t is minus infinity or something. So, this has to be 0. So, then you will just write r square plus pr plus q is equal to 0. This is what is called the characteristic equation. Okay, and then you can solve this quadratic equation. R is equal to minus p plus or minus p square minus 4q by 2. Yeah, you can solve that and then you will get r. So, you will get two values of r. So, then y1 is e to the power of r1t, let us call this two values r1, r2, and y2 is just e to the power of r2t. Okay. So, you have two solutions, r presumably is different for the two cases, and you can take this out and then you will see if you take this y1 by 2, the w of y1 by 2 at Wronskian w of t, which is y1 y2 prime minus y2 y1 prime, that is non-zero in general if r1 is not equal to r2. If r1 is equal to r2, you have to be a little careful, we will come to that later. Okay. If this is not the case, then this is not equal to 0, r1 not equal to r2, and you have got two y's and then you put that in. Okay, general solution is done. Okay. Now, I would like to discuss a few things about this procedure that probably never thought about before. At least I never thought about it before, and it makes a lot of sense when you think about it in this framework. The first is the following. Why do you do this? Okay, why do we do that? Now, remember I said the reason why these equations are complicated is because you can't factor them. And the reason you can't factor them is, like we said, twofold. The first is the factorization is not unique, right? We had that tan hyperbolic example. So, the factorization is not unique. But even if you were to account for that and say, okay, fine, I'll factorize it and so on, the second step we were going around in circles. So, there is no way to get a general p and q and then do this stuff. Okay? Except when p and q are constants. Okay? When p and q are constants, then you can presumably think of this as being comprised of d plus a times d plus b, where a and b are now constants. Okay, remember. And if you do that, then you can automatically break that entire thing into two. Remember that example, maybe that is a little bit more instructive. Let me go back to the example that I brought up. Let us look at this example. So, if I had d square y by dt square minus 1 minus y is equal to 0. This is okay, it is kind of similar to this, where it is even more simpler because q naught is minus 1, p naught is 0. But if you take this guy, you can write this down as dy by dt plus 1 dy by dt minus 1 times y. Okay. Now, of course, going from this step to this step, like we said, is not unique. The tan hyperbolic guy will also give you the same value over here. But if you leave that out, if you say, okay, I'm willing to deal with non-uniqueness problem because of all the possible candidates, I have to pick one. I'm picking this because it seems the least troublesome, right? If you do that, then you can do what we had originally set out to do, call this W. So, then sorry, this is d by dt. Okay, call this W, then we will have dw by dt plus w equals 0, and you get w is exponential of minus t with a constant. Okay, constant does not matter, I am going to throw it out, and you put that back in here, you will get dy by dt minus y is exponential minus t. And you can solve for this. Okay. Now, if you remember, when we did this equation, I had a little detour and I told you about that yc and yp. You remember that? Yc, yp over there. Yeah. The solution to this problem has the two parts. The yc was the complementary part where I set the right hand side equal to 0 and did this. And the yp was this part, the solution to this entire exact full problem. I discussed that when we were starting our discussion about first order systems. If you go back there and you apply that same idea to this, you will see that the y1 and y2 that you get as a result of this are basically just those two. Okay? Because already you can see yc is dy by dt is equal to e to the power of t from here. Okay? E to the power of t. If I did the same procedure here, I will get, if I put, like I said here, if I do the put y equals e power rt root, then I will get y1, so I will get r square minus 1, r equals plus or minus 1, that is y1 is e to the power of t, y2 is e to the power of minus t. Okay. E to the power of t is yc over here, and e to the power of minus c is presumably yp, or in a more general case a linear combination of yc and yp. Okay. So, this yc and yp serve to give you the y1 and y2. Okay. And the reason that happens is because when you have constant coefficients, factoring becomes easier. You can in general factor, and this factoring is precisely the reason why you do this, to figure out the factoring. Okay, that is what you are doing here, you are figuring out the factoring by doing this. So, this is done to figure out the factoring. And what factoring are we talking about? We are talking about this to d plus a, d plus b, right? That factoring which we tried so hard for the general case but did not work. Yeah, so this is a shorthand way of figuring that out for a constant coefficient case, which is why it works. Okay, so that's just a little detour, so you know why on earth you are doing this seemingly bizarre looking substitution, but it works. Okay, good. So first order constant coefficient is okay, it's easy enough to do, the simplest case. Let me do a slightly more complicated case. Sorry, I mean second order constant coefficient is easy enough to do. Let me do something slightly more complicated than this. Let's say I have, okay, and presumably you can do all sorts of systems with this. You have this, and you have spring with a mass, and you have a damper like this. And you can basically, if you spring constant is k, damping coefficient is c, you have m, you can measure the y from an equilibrium position. This will be a second order differential equation like the one we just wrote down, plus p of t. P of t will be constant of course here, because it will depend on all of these different parameters. Okay. And now you know how to solve this guy. You can come back and do problems in vibration and so on. You've probably done this also at some point in your life. And the vibration problem, again you give initial conditions for this case. It's an initial value problem because you specify the position and the velocity at which you let the mass go, and it does its oscillation thing. You don't specify the initial position at t equals t0 and the final position at t equals t1. So this is a classical initial value problem. Okay. And now we know how to solve this. Now there is a variation of this problem, of course, which you have probably also seen. You probably, maybe some of you have also solved. which is I don't let this go like this, but I apply a force. It's a function of t. Okay, so I don't just pull and let go, so it's not just doing its own stuff, which is called the free vibration problem incidentally. But instead I put a force as a function of t, and then I see how this guy is going to move. Now, if the spring were not there, damper were not there, then this is going to move exactly how F makes it move, right? So you'll have d square m d square y by dt square is equal to f of t. This is Newton's law. But now it becomes a little bit more complicated, because you will now have an equation that looks like this. Oh, sorry, which looks like this. So if you, like I said, if you don't have the spring and the damper, if you don't have the damper, you will get this guy off. Okay, if you don't have the spring, then this guy is also off. So then you will only have Newton's law, which is f of t is d square by m times d square y by dt square. Doesn't matter. Put an m. Let me just call this small f. Okay, small f of t, just to make things easier for us. And you have to solve this problem to get y. Now this internal compliance and damping and so on is going to make y non-trivial. It's not going to follow f exactly, but it's going to have a little shift from f, and that shift is what you want to find. And this is where our discussion about that yc yp business becomes the generality of our discussion of the yc yp business becomes clear. Okay, so what do you do in this case? Well, you do two things. First is you look at RHS equals 0. This is called the homogeneous problem. Okay, so you solve the homogeneous problem for f of t equals 0. This f of t equals 0. So no forcing. We know how to solve that. So you will get solution of the homogeneous problem, which I am going to call yh, is equal to c1 y1 plus c2 y2, and again y1 and y2 are done by putting that exponential rt thing into this and then solving and so on. Yeah, so you go y1 y2, you know how this is, you know y1, you know y2, so you know yh, you know the initial conditions where you're going to let it go or whatever. You still need initial conditions, even though you're forcing, you need to start it from somewhere with some velocity before you start forcing. So you still need initial conditions here, and so you can get c1 and c2 from here, and so okay, the problem is solved. And now you look for a solution yp of t that obeys this. Okay, it obeys, let's call this equation 1. So the yh obeys, let's call this 2, the homogeneous equivalent of this. So yh obeys 2, yp obeys 1. So the general solution in this case, forcing case, is y is equal to yc plus yp. Why is that? Because when you take general solution has to obey 1, this equation, the forcing equation, forced equation, whatever. When you put this into the left hand side, the left hand side stuff acting on yc will give me 0 because yc obeys 2. Left hand side acting on yp will give me f because yp obeys 1. So that is the general solution. Okay, and notice that the not yc, yh. And notice that the constants c1 and c2 are in yh. They are not anywhere else, right? They are in yh. Okay, so the yp does not have any freedom to satisfy the initial conditions. The yp is a property of the differential equation. It's not dependent on the initial conditions that you have here. The general solution is, but not the particular solution. Okay, the yp incidentally, okay, it's also called the particular solution. I think I should give you these names so that you remember them. This is exactly what we did for the 1D case. If you remember, if you go back and look at that, that's exactly what we did. We split the thing into 2, and then the yc had one unknown function, and then that was what we'd used, and then we said okay, yp and so on. Yeah. That was the general solution. Good. So far we know how to get y1, y2 and yh for this problem, but we don't know how to get yp. Okay, and that is the subject of what is called the method of variation of parameters. I'll start this today and then we'll continue this and move on to more general techniques for first order system for second order systems without constant coefficients. This is all for constant coefficients, remember. So we know YH. How do we get YP? Okay, and this is a standard technique you can use. Right, YP is equal to U1 Y1 plus U2 Y2. U1 and U2 are unknown functions. Okay, Y1 and Y2 of course are known because they are solutions of the homogeneous equation, equation 2. And if you write it like this, you basically put this back into equation 1, which we had written here. Okay, and you see what you get. First, let's do the first derivative, dyp by dt. This is u1 prime y1 plus u1 y1 prime plus u2 prime y2 plus u2 y2 prime. Okay, that's what dyp by dt is, and then you can take the second derivative of this. Prime is d by dt. Okay, that's, I'm just using shorthand because it's a little bit tedious and I'm running out of chalk. So this will be u1 double prime y1 plus u1 prime y1 prime plus another u1 prime y1 prime plus here, that will give you 2 plus u1 y1 double prime plus u2 prime y2 double prime by 2 plus 2 u2 y2 prime prime plus u2 y2 double prime. Okay, that's what this is. Okay, and if you put this back into, let's write down the original equation. Original equation was let me get rid of this, we don't need this. The original equation was p square y by dt square plus p of t, p naught, sorry, p naught dy by dt plus q naught times y is equal to small f of t. Okay, so if I take this guy and put it back here, I'm going to get u1 double prime y1 plus u2 double prime y2, which is here, plus so I've gotten rid of this, plus 2 u1 prime y1 prime plus 2 u2 prime y2 prime. Now I've gotten rid of this and this, I only have the last term, so I'll have u1 y1 double prime plus u2 y2 double prime. That's the first term, this guy, and then I will add to this the second term, which is p times this guy, u1 prime y1 plus u1 y1 prime plus u2 prime y2 plus u2 y2 prime. Okay, and then I'll add the third term to that, which is just q times u1 y1 plus u2 y2 is equal to f. Okay, so I've only taken these two things and put it there. Let me make sure I don't have any terms missing or any additional terms. 1 by 2 blah blah 1 2 3 4 5 6. Yeah, good, you've got all of them. Okay, if I do that, then some terms will come out. Now remember, y1 and y2 solve the homogeneous problem. That was equation 2. Okay, so let me write down this is equation 1, and then equation 2 was the homogeneous fellow. This is equation 2. So y1, y2 satisfy this. Let's keep that in mind. So if I go and open this guy up, I will get u1 times y1 double prime plus py1 prime plus q y1. So I'm going to get rid of this term, and this term. Those three terms are gone, taken care of them here. Plus u2 times plus py2 prime plus q by 2. Now I've gotten rid of this term, and this term. Okay, plus what else do I have? I have u1 double prime y1 plus u2 double prime y2 plus 2 u1 y1 plus 2 u2 prime y2 prime. I have these four now. Okay, plus p times u1 prime y1 plus u2 prime y2 is equal to f. Okay, so this guy, these two fellows in brackets are 0 because y1 and y2 satisfy 2, and this is exactly 2. Left hand side of 2, right hand side of 2 is 0. So this is 0. This is also 0, of course, because y1 by 2. So you're left with this. Okay, now you're in an interesting dilemma. You say, okay, I have two unknown functions. I've written p in terms of two unknown functions, whatever they are, but I have only one equation, right? I have only one equation to determine the two unknown functions, which is this. So I still have some freedom in picking these two unknown functions. There is still some freedom, two functions, but I have only one equation, right, to solve. So what's going on here? I have freedom to pick the other one. So in order to exhaust this freedom, we'll go back to where we started. We said yp is u1, y1. I'm going to get rid of this now. So we have two unknown functions, but only one equation. Okay, so we go back to our original guy, that is yp is u1 y1 plus u2 y2. Okay, and we see, okay, what can we do here to make sure that we exhaust or give another condition so that we can get a unique value for u1 and u2. This freedom is still there, right? We need to enforce another equation so that we'll have two equations for two unknowns, and we can actually solve for u and u2. And then once we do that, the problem is solved, right? So if we do that, let's go here. Remember, dyp by dt was u1 prime y1 plus u2 prime y2 plus u1 y1 prime plus u2 y2 prime. At this stage, if I set this is equal to 0, then I have another condition. Okay, I can use that condition, that is an equation now. If I use this, oh sorry, not this, I have to set this equal to 0. If I set this equal to 0, I'll get another equation. Okay, I already have one equation, but if I set this, I'll get another equation. Why would I want to do that? Well, remember, when I took this derivative, I had the combination of terms which had a derivative on y and a derivative on u. The terms that had a derivative on y will anyway go away because they'll go into p's. Remember, it was p naught times, this is all p naught, q naught, whatever. It was p naught times this term, p naught times this term. Those terms are anyway going away to 0 because y1 and y2 obey the homogeneous equation. So those two terms I don't have to worry about. So these are the terms that are making the redundancy more and more complicated. So what if I just set them equal to 0? Okay, if I set this sum of these two terms equal to 0, I will have two equations, one coming from the final expression from the ODE itself, this is number 1, and second is this. So let's try that out. So if I do that, now d square yp by dt square is presumably easier because it's only that guy. So I'll only have terms like u1 prime y1 prime plus u1 y1 double prime plus u2 prime y2 prime plus u2 y2 double prime. Again, these two terms are going to go away because those are these two terms. They are anyway going to go away to 0. They are multiplied by u1 and u2. So the only term I will now have remaining, if I put this again back into the differential equation, I will now get two equations. One will be u1 prime y1 prime plus u2 prime y2 prime. This is this, okay, is equal to f. That's the only thing remaining, of course, we don't have anything else. And the second, of course, is this, because now I have enforced this, which is u1 prime y1 plus u2 prime y2 is equal to 0. Okay. So now I have two equations, I have two unknowns, I can solve for them and I can get a result. Okay. So what we'll do next in the next session is we'll start from here. I'll go through this, maybe for continuity I'll start from here again, and we'll see what this gives us. Okay, it turns out that this is linked to the Wronskian that we introduced at the start. So as long as y1 and y2 are linearly independent, the homogeneous equation of the solution of the homogeneous equation number 2, then you can get unique values or unique functions u1 and u2 such that yp is u1 y1 plus u2 y2, and once you know this, once you know u1 and u2, you know yp. Once you know yp, you can add it to yh and get the general solution to the equation. So this equation 1 is also solvable, okay, in closed form. Not just 2, even 1 is solvable, and we'll see, we'll work out this last bit of algebra in the next session. I'll show you how to get an expression for the general solution y. Okay, so that problem will be solved. Once we do that, we'll look at the more general case. Okay, slightly more general case. We'll look at the homogeneous problem where p and q are not constant, and then we'll see under what conditions can we get a solution. How is a solution usable? What can we do? Okay. Now there are a series of tricks you can do for any given linear ODE. You can do a series of substitutions. You look up a handbook, you will find these substitutions. You can convert them to one form from another form, and it really will be a waste of time if I were to just enumerate all of these substitutions because they are not really of general utility. So what we'll do is we'll assume that we have access to these transformations, that we can do them if needed for specific values, specific forms of p of t and q of t. But instead what we'll focus on is if for the general problem I give you one solution, let's say either y1 or y2, can you from there get y2, and from y1 and y2 can you get yp, just like we did for this case. Okay, that's the next sort of general question that we can ask for arbitrary p and arbitrary q which are not just constant. For the constant case, it's solved, the problem is solved. Okay, whether it's equal to 0 homogeneous, not equal to 0 inhomogeneous. Okay, so we'll start off from here, we'll finish this last bit of algebra and then we'll continue on to the more general second order linear system in the next.